Hello, this is Professor Alan Haungs, and this will be the oscilloscope basic concept number 3 for the Physics 124 SUNY at Fredonia, our oscilloscope lab. This concept will be concerning the time base, using a time base. And I'm going to actually have you do a little simple calculation. I'm trying to make it interesting, so it's something you might enjoy. Because this is kind of dry if you don't have any application, so I thought up an application. So where you are physically located right now is... that's squeaky, huh? Well, let's see if I can loosen that up. You're in my basement. You're in my laboratory in my basement. That's where you are right now. I hope that noise isn't too loud. That's my fancy dancy oscillator or signal generator. You can make all the different kind of waveforms with it. That's my old school oscilloscope. See if I can adjust the, here we go. There we go. That's my oscilloscope with all the controls. And that's the time base. So that's time per division. This is the voltage gain. Okay. So I'm going to make a very interesting demonstration to you. I think you'll enjoy this. So there's a waveform right there. Let's see if I can zoom in good. So you can see it. Maybe I'll even turn the lights off so you can see it better. And I'll go like this. See if I get right on top of it, so you can get the best view. Okay. So you probably wonder what you're looking at here, or maybe you don't care, but I think you'll enjoy this. So, once you establish something like this, and you stabilize the picture, you can kind of move it up and down. You can reposition it. Now I'm playing with the trigger right now, so I might lose it. See, it gets stronger, weaker. There's stuff you can do to kind of goof it up. See, so if I'm playing with the trigger, I get the cleanest picture I can, and then you kind of leave it alone. So that's the trigger. Here's the time base. If I change different positions, you see I get da 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 da. So that's, that's obviously too broad. Okay, that gives you an idea of something. Now, if I play with the voltage divisions, I could go like this. It's too high. It's distorting it. Too high, too high. Okay, so I have it at a very desensitized level. What you're looking at here is a radio frequency, and you're going to actually calculate this radio frequency. And how can I prove this is a radio frequency? Well, it's actually a radio frequency. It's an AM radio frequency that's used for broadcasting for AM stations. And what I did is I'm modulating it with a audio signal. So this is the audio. See that right there? That envelope is the audio signal, the part that goes around it. So those real fast parts, that's the radio signal. You hook that up to an antenna, which I did, and right now I'm broadcasting this audio signal over the airwave. And so if you were to drive in front of my house right now and you had your radio tuned to this station, you would hear this annoying tone. You think, is that really possible? Did I really do that? Yeah, that's pretty possible. Pretty easy, actually. So what we'll do is we'll turn on our AM radio, and I'll demonstrate it for you. So we happen to have an AM radio over yonder. We'll tune it, turn it on. So let's now adjust the wave, the actual frequency. I have just overrode their radio broadcast. If you don't think, see what I'm doing? That's me. That's us. That's me. That's just I'm varying the tone. See? I'm varying the tone. I can make it real annoying. So I can do all kinds of annoying things. So right now, if you were to drive in front of my house, that's what you might hear if you were listening to that radio station. Okay? So this little lesson or demonstration is on time base. So you're going to tell me what radio station, what AM radio station, what's its frequencies. Usually the frequencies on the dial are listed in kilohertz. You can give it to me in megahertz. I don't care what units you use. But you're going to tell me what is the broadcast of that particular radio signal. Let me see if I can get it close. I know it sounds like a World War II thing, right? That's because a lot of this is kind of World War II-ish. Okay, so I'll turn all that off so you're not going crazy. Okay, so let's zoom in at those real high frequency components, and you're going to tell me what radio station this is. So what I did is I adjusted this, the time scale, the time division. I adjusted it to 0.2 microseconds. Write that down. 0.2 microseconds. Okay? That's important. Now, frequency equals 1 divided by the period. The period on a sine wave is how long does it take to repeat itself. That's called a period. So frequency, which is what I'm asking you to find, is 1 divided by the period. So we know that since I adjusted this to 0.2 microseconds per division. So these are divisions, these major things are divisions. All those are divisions. So what I'll do is I'll kind of get this situated nicely. Play around a little bit. So what we want to know is from here, that's one complete cycle, to here, how many divisions there are. And each division, like I said, is 0.2 microseconds. So what you do is count the divisions as best you can. And estimate this one right here. Just estimate it as best as you can. Okay? That's the total time for a period. So frequency, this also in your lab manual too. The formula is in your lab manual. So the frequency is 1 divided by the total time period for that cycle. That frequency is what that radio station was being broadcast at. So I want you to tell me what the AM frequency is. I don't know if you can, if you're close enough, you might even be able to Google it and even find out the call letters of that radio station in Buffalo, New York. But that'd be I'll give you extra credit if you do that. But you're just going to you can get pretty close. I did a calculation and I got pretty darn close. So so should you. Now let's use the, now I want also you to calculate for me. So I'm going to then take this and I'm going to turn the time base down so that I can actually see what the audio, what was the audio signal that I was putting out that I was annoying everybody with. So that looks like a good one right there. Okay. So I got this here. Okay, that's there. Okay, got this to here. You can see I can put out different frequencies. So what I want you to do is you're going to, I'll position this. Now this is an example. Now normally you don't put out a tone. You don't broadcast a tone when you do a radio broadcast. You put out your, you put out a voice signal. This would have been an example had I modulated this with a voice signal, not a solid tone. This would have been an example of a periodic and a non-periodic behavior. But these are both periodics. But had it been a voice, I'll show you a non-periodic in a different demonstration. So this is the audio tone that we're using. So we're multiplying the audio signal times the radio signal. Radio signal's this. So you're going to tell me that frequency. Then you're going to tell me this audio frequency. So it's right now it's set at okay, I'll say it this way, 0.2 milliseconds. Okay? That's what I set the time division for. Okay? So each of these divisions is 0.2 microseconds. I should have said 0.2, I'm sorry, milliseconds. Oh my goodness. I'm going to get everything confused. Okay. The earlier one was set at 0.2 microseconds. This one is set at so for the radio frequency it was 0.2 microseconds. This one is set for 0.2 milliseconds. So that's per division. So I kind of set it up. So each of these divisions is 0.2 milliseconds. So from 1 all the way to the end, I want you to estimate the total period of one cycle. And you're going to tell me that frequency, and that was the annoying frequency that I am right now broadcasting. Still doing that. I think I'm still doing it. Yep. Yeah, that's my AM radio. Hear it? That's AM radio. So I'm still broadcasting that frequency tone over that frequency radio station. You're going to include that, so that'll be your question number 1. That's so we're doing a time base and a period, so you're calculating the frequency and the period by using the time base on the scope. We'll see how this works. Alan Haungs, Oscilloscope, basic concept number 3, physics 124, SUNY of Fredonia. Good luck, guys.